questions from what we've talked about so far? So lecture 1 was kind of overview, motivation, example to show our linear spectroscopy methods. Lecture 2 was the introduction to diatomic molecules and how we can bypass quantum mechanics and get to positions of lines. Remember, we're focusing now on positions of lines. Positions, strengths, shapes. A lot of time on positions. And it escalates rapidly. So we did what I would call row vibrational. Combined rotation vibration is called row vibrational. What happens when we change the electronic state? Now it becomes row vibronic. Every time we add another layer, it gets more complicated. We start with a simple rotation, really simple. Rotation vibration, pretty simple. Go to electronic, row vibronic, it gets complicated fast. It gets complicated in different ways. It depends on the properties of the molecule. So some of these slides come out of my lecture course, Stanford, on spectroscopy. And I usually will start my lecture with some sort of a picture of some kind that kind of motivates what we're trying to do for today. What is this picture? And I apologize for blocking you. I can't see the one over here. This is a plot now of the strengths. So the height of these lines is a measure of how strong the transition is. These are OH line strengths. So OH is an important species in combustion. It's a radical species, so it facilitates chemical reactions. So it's a species that we would like to measure. And it's a species that was responsible for some of the lines in the spectrum that I showed you earlier. Now this is a function of wavelength in nanometers. So this goes between 306 and 310 nanometers. So remember, your eyes only work from, say, 400 out. So this is the ultraviolet. You can't see this, but they're there. And 300 nanometers corresponds to approximately 4 electron volts. We're now talking about a lot of energy. And so in a flame, there would be small populations of the molecules, excitatory molecules that would emit, but nonetheless they are there because of chemiluminescence. So the chemical reactions sometimes take the energy of the reaction and give it to the product in an excited state so that it emits, and that's called chemiluminescence. Well, in any case, we'd like to characterize OH, and we have to understand not only the positions of the lines, we have to characterize their strengths. But this is a plot, kind of a master plot, which combines the strengths and positions. So now what we can see is that there are like 6 primary groupings. Here's one group, here's another group. So instead of having 2 branches, which we had for carbon monoxide, 2 branches, P and R, now when we go to electronic transitions, it gets more complicated. Now we're going to have P, Q, and R. Somebody was asking about this. Why don't we see any lines at the null gap? That's because the quantum mechanics told us that for those molecules, delta J had to be plus or minus 1. No delta J of 0 was allowed, in the case I showed you. That's why there was a gap. But when we go to these electronic spectra, you can have delta J's. And now all of a sudden we've got P branches, Q branches, and R branches. So there's going to be 3. But it's even more complicated because OH is a molecule that has what's called a turn symbol. These are symbols. Spectroscopy is a lot of symbols. And this tells me that these are the transitions from the ground electronic state denoted by an X to the first excited state of the same multiplicity, which is why these 2 is there. And that this state has a property called pi, and this state has a property called sigma, and these are the 0 here. There's a lot of meat here. These are the lines that you see at 2,000 degrees. Now, I plotted this at 2,000 because the strengths of the lines change with temperature. Because the Boltzmann distribution changes with temperature. The positions don't change, but the strengths change. So, this is a calculation that the students would do in my question course. There would be a homework assignment, but not a big homework assignment. And so on here are the P, Q, and the R's, and it's complicated because when I see this pi, that means trouble. If I see a sigma, good. When I see this pi, there's another factor of 2 running around. So instead of having 3 branches, there's 6. So things kind of scale up fast. So start simple. So this is the sort of thing that would be kind of like a research problem. If you wanted to measure OH, this is something you might have to dig into. I'm going to talk about a number of things here in this. So this is like the capstone that we won't get to today. But there's some potential energy wells, rotational analysis. So this is an overview of electronic spectra, basically. Diatomic molecules. So we did this before. So if we had nitrogen, it would have a variety of possible electron configurations. You change the orbit of the one electron and you change the energy. And so there's a progression from the lowest energy state, called X, to the first one, called A, second one B, next one C. As you change A, B, C, you'll notice that the 3 stays there. So as long as that 3 stays there, we use capital letters. If you change that 3, you got to go to lowercase letters. These sigmas tell me things, as do the plus and the U. But really, unless you want to get into quantum mechanics, you just kind of don't worry about this stuff. Okay, so there's a lot of information. Now, all of this is based on the idea of a potential energy well. So we talked about this. This is the repulsive side of the potential energy well and the attractive side. So you're way out here, atoms come together, they're on a line, and they start attracting each other. They're going faster and faster and faster as they go down this potential energy well. So down here, potential energy is at the minimum, and the kinetic energy is at a maximum. They're going like crazy. Now they start getting together, and these electrons start repelling each other. It's called the repulsive side. So it comes together, and then it comes to a stop. The energy stored in that in those charge energies is equal to the original energy that came in. So it goes to here and it goes back out. That's what would happen if you were really low pressures and there's no chance for a collision. But if sometime during that process you have a collision here, it takes away some of the energy, it no longer can get back out. It gets trapped. And so most molecules live down here. And they don't get out unless you put them to really high temperature. Or really what happens is you have a molecule and in comes a colliding partner and it's got a lot of kinetic energy. Bang, rips it apart. Conservation of energy applies. So that's how we think about this. So we're really talking about potential energy wells. Now you can do this with a diatomic molecule because there's only one length for it. As soon as you go to a triatomic molecule, now I got trouble. I got 2 different lengths to worry about, and orientation. So you have to kind of start here and it gets harder as you go to polyatomic. So when you change the electron configurations, you change the shapes of these wells. But it only can jump from one to the other. It's not a continuous change. So the electrons have to be in specific orbits. Change to the next specific orbit, it's got more energy. So if you saw the hydrogen atom when you were taking physics, undergraduate physics, I guess, you would know that there's different allowed energies and different quantum numbers. As you get further and further, the nucleus energy go up. That's what's important to think about. Okay, so now let's imagine we have 2 of these potential energy wells. This is the lowest one. Here's the next one up. Bunch of notation. So this is how we define all the different terms. E denotes the equilibrium position. This is RE double prime. This would be RE single prime. Single prime upper state, double prime lower state. The dissociation energy is usually measured relative to the bottom of this well, so that would be D. E double. This energy right here would be E prime. That's the energy required to pull this molecule apart. When these 2 molecules are pulled apart, we end up with something rather different. The atoms that you produced are actually different. The atoms that are produced here are not the same as the atoms here because this one's got more energy. It's a different atomic configuration. And that is called EX. A lot of notation. Frequencies, energies, here's the minimum, kind of between V equals 0 and V equals 0. So we care about these numbers. This is X, this is V. So that's a quick introduction to potential energy wells. So usually we're talking about the same so-called multiplicity. X is the ground state, A is the first excited state of the same multiplicity. T is usually a total energy, and here it's called the term energy. It's the difference between the minimum here and this minimum. So that's the minimum energy that it would take. Well, that's the energy difference between these 2 minimums. Now we can also look at the energies that are required to bring about change. So let's say you're at room temperature here and you're in this level. If you send in photons of energy greater than nu max, you're sending in so much energy that you can not only excite this molecule, you can dissociate it. So there's some interpretation to these frequencies. Why do I care? Basically, if you look at the spectrum, the spectroscopist can look at the spectrum, infer these numbers, and start deciding these numbers. The spectroscopist would figure out what is the dissociation energy, what is the value of RCD, what is the dissociation energy. So basically, you piece together a picture of these molecules by looking at these energies. Okay, so we have to be careful. These D's now are the dissociation energies. They're not the distortion constants that I talked to you earlier about for the rotational energy. Sometimes it's good to think about characteristic times in problems. So you're doing some combustion problem, and you're worried about non-equilibrium. And maybe you think about, well, people who do plasma-enhanced combustion have to worry about a range of time scales. They might want to worry about sub-nanosecond processes while plasma is heating. Or maybe they want to care about milliseconds on which a chemical reaction takes place. You can simplify your mental model sometimes by saying, I only care about long times, I don't care about short times. Some processes can be approximated in different ways. So if you think about the time it takes to move electrons, that's a short time, like let's just say 10 to the minus, I think that's a 15 or 16. It's short number. Electrons move fast. And less. 16, you can see that. Okay, so if you talk about the characteristic time for one vibration, you might get a number of about 10 to the minus 13. You might think about occlusion, you can think about it and say, well, it takes about 10 to the minus 12 seconds. Depends on how you do that. How long does it take to rotate one time? Maybe about 10 to the minus 10 seconds. What about the time it takes for a molecule to emit? So if you put a molecule in an excited state and you leave it alone, it will spontaneously emit on average time. That's called radiative lifetime. And that might be time between 10 to the minus 6, maybe 10 to the minus, depends on what it is, but a few tenths of a second. Notice a wide range of times. So depending on what you're thinking about, you might be able to make certain approximations of the other activities. That's thinking about characteristic times is a good way to deal with a lot of problems that have multiple time scales. The Frank-Condon principle is one of the primary principles of looking at spectrum. It says that because this electronic time, the time it takes to change orbits, is really small, we probably move on this potential energy diagram between one point at fixed r. In other words, it happens so fast that the energy we're facing hasn't changed. That the transitions occur on vertical lines on this diagram. That's the principle. That's helpful. So that just says that if you happen to be a molecule that's living right here at an instant time, and you undergo an electronic configuration change, you move straight up somewhere onto this upper curve. And so if you're at v equals 0, where on average you're in the middle, you're going to go vertical. Now where will you go? You have to go to a place where there's an absorption transition. It has to be an allowed state. So the Frank-Condon principle kind of simplifies the picture and says we only really have to worry about vertical lines. This is tied to the selection rule idea. Selection rule have only delta V of 1, only delta J plus or minus 1. Now we're talking about electronics. And it just says the electronic changes that take place occur at constant R. So if you were a molecule that you're vibrating in a well, where do you spend most of your time? Where do you spend the least of your time? The minimum, because you're going so fast. You go right through that minimum. But most of your time trying to turn around. Pull, So you spend most of your time at the ends. And therefore, there's going to be a high probability of absorption when you have an end that matches a vertical line with another end. This is an approximation. And so this Frank-Condon principle is how we think about vibrational rules in electronic transitions. So for pure rho vibrational, delta V is 1, delta J is plus or minus 1. But now we're going to have electronic transitions. What are the allowed delta V's? It's tricky. So the Frank-Condon principle is a way to help sort this out. And what we'll find is that there will be, if you're down here, there will be multiple solutions. It's not just delta V, it's zero, 1, 2, 3. And it depends on the placement of this well relative to this placement. If this upper well looks exactly like this one moved vertically, that's different than if this upper well has a value for RE that's quite different. It makes a lot of difference. And so the people have sorted this out by the Frank-Condon principle. So once you know the shape and position of this well, you can begin to specify the relative probabilities of certain vibrational change. That's just saying in words. The vertical lines represent electronic transitions of constant R, and those are the ones that are safe. Now, another thing to think about is that, what about collisions? Collisions are how we change vibrational fundamental. So, molecule is vibrating, and in comes a collider. This molecule, left to itself, is just vibrating and rotating and moving through space. Along comes a collision partner. If they collide and the partner, conservation of energy applied. If they collide and the partner goes off with the same kinetic energy it had initially, elastic collision. If it goes away with different kinetic energy, inelastic collision. So something happened to these quantum states. Which of the transitions for which of the favor is the vibrational change state? So imagine a oscillating molecule, and here comes an atom along the axis. It's going to come in and it's going to bang on this molecule. And it turns out that the probability of the change in vibrational quantum number is enhanced if the time period of that interaction is the same as the vibrational period. That's a complicated thing to show mathematically, but it's true. Therefore, we care a lot about these characteristic times. What this usually means is since this collision, this vibrational frequency is pretty high, 10 to the 13th. Turns out you have to have a high speed collision to make the vibrational change. So that means there's a certain velocity range of incoming particles that will be favored. So this helps us understand when do we have vibrational equilibrium or not. Because how do you get vibrational equilibrium? Through collisions. Collisions maintain the Boltzmann distribution. Take away the collisions, everything breaks down. So it's collisions, and I told you there's 10 to the 10th for my nitrogen molecules in each room. A lot of collisions. So it's collisions that maintain the Boltzmann distribution. But it takes a certain kind of collision to bring about vibration. It's harder, only a small fraction of the colliding molecules have enough energy to make this happen. So you need high collision frequency total in order to have this process. Okay. This leads us to the idea that we can have either discrete or continuous spectrum. So here's two electronic states. And they're designed here so that the minima have about the same value of RE. Frank-Condon principle tells us that we're going to look at the ends and we're going to draw up here and we're going to see if we come close to an end. That's going to be a favored collision. That's going to be a favored transition. We're going to go from 2 to 4. I'm going to go from maybe this 2 over here, maybe to this 2. So because the REs are equal, the bottom kind of lines up here. So that just means that I can already get a feeling for the most favorable vibrational transitions. So whereas in vibrational spectra, the rules are simple, delta V is 1. For electronic spectra, all bets are off. It now depends upon all these other things. So you can have multiple vibrational transitions given by the Frank-Condon principle, and they're expressed in the table called the Frank-Condon factors. They can be calculated or measured. But this says the relative probability. I look at that table and I can say the relative probability of going from here, from 0 to 0, or 0 to 1, or 0 to 2. That table would give this to me. Where did I get that table? Somebody measured it, or the quantum mechanics guys calculated it. They calculated it by knowing all these parameters of the molecule. Now, the people doing these calculations don't know how long it takes. So there's you can calculate chemical equilibrium. If you had combustion, of course, you would calculate chemical equilibrium. put together some hydrogen, some oxygen, specify pressure and temperature. You can calculate the final composition. But you can't tell me how long it takes. That's a kinetics problem. So there's all these different branches of science. There's thermochemistry, statistical mechanics, spectroscopy, and chemical kinetics, and they all relate. But some things we're talking about, we don't know how long it's going to take to get something different to get that. So we can have continuous spectra, or we can have discrete spectra. Now, we have two wells like this. What would our absorption spectrum look like? Well, we're going to see some lines here that would begin minimum energy here to be zero. So if we're going in frequency this way, we begin to see some absorption here, sort of oscillating character. What happens when we start sending in photons which have delta? Oh, now we get a continuum. There's no discrete states in here. So when you send in more than delta, there's only continuum states. So from this spectrum already, the spectroscopists can say, I just determined new zero, I just determined delta. And if they looked really carefully in this pattern, they might also begin to get these Frank-Hunt factors. There's another case. What happens if the upper state has this character? It's called a purely repulsive state. You take two atoms that come together, they don't like each other. They will not attract, they only repel. It's because of the electron calculus. That's called a purely repulsive state. They exist. They're very short-lived. They come together, they go back apart. If during that process there's a collision, they might drop down here. So you have to keep in mind that these atoms are a little different. One or both of these atoms are different than these up here. But what does the spectrum look like when you have a case like this? Well, you can only have a continuous spectrum. So if you look and you see it only has a continuous spectrum, there's a clue that it's a repulsive state. So the difference between the right-hand side and the left-hand side. So gradually over time, people determine these properties of the molecules. And of course, once they're known, they don't change. This is the spectrum I showed you early on this morning, which is one we measure in my lab class. And now these numbers might start making a little more sense. These numbers correspond to the vibrational levels, V prime and V double prime of these features. And this is nitrogen. This is the so-called first positive system. So if you measure these things, eventually you could figure out these vibrational spaces. Remember, the first one is V prime, and the second one is V double prime. So gradually the spectroscopists look at different experiments and they figure out the properties of these molecules using stuff like this. Now I'm going to show you how they do so-called rotational analysis. What are the parameters in this problem? TE, RE, omega E. So if you're doing vibration rotation, it's omega E and X. If you're doing the rotations, BE and alpha. So really, four. But now if we go to electronic, I've got some more. I need to know T sub E, the difference between these wells. I also care about RE. So we can take the spectrum, the emission or absorption spectrum, and sort it out. T is almost always reserved for the total. So the total energy would be the sum of the rotation, vibration, electronic. So for the upper state, that would be F of J prime, G of B prime. That should be G of B prime plus the upper state. What's T sub E for the ground state? Zero. So by convention, the lowest ground electronic state is the T value of zero. So this is the energy of the upper state expressed in terms of B and J, omega E, and X. If I want to get tricky, this could be also a B sub B prime. We do the same thing for the lower state. And if you think about, if I'm going to analyze a particular band, just one of those broad features, a given band, all of this would be a constant. It just depends upon omega E and X. So whatever is constant. And the same for the lower state is constant. So that just means that if I take the difference between the upper state and the lower state, and I do rotational analysis, I'm just looking at the lines within one band. I can do that because I'm after the difference between the B's. When after rotational analysis, you're after the B's. Vibrational analysis, you're after the negatives. There can be a bandhead. So if you ask, if I take the derivative with respect to m, I need to say what m is. So when you do rotational analysis, you let m be minus j in the P branch and j plus 1 in the R branch, so that all these lines collapse into one distribution. You take the derivative with respect to m, and you can solve for the bandhead, and it depends upon this number right here, this delta. So this is minus, okay, the m is the bandhead. This could be either a positive or a negative number, depending upon whether RE prime is higher or smaller than RE. So remember, B is 1 over I. I is R squared. So if R gets bigger, B gets smaller. So if RE prime is bigger, then B is going to be smaller, and that B prime is going to be smaller. This is going to be a positive number. Because the converse is true. If the upper state has a small r, E, then its B is going to be small. It's going to be, would be bigger, okay, be negative. So you can have a bandhead. So an electronic spectrum, real harmonic spectrum, there's a lot of bandheads. And you can tell them it can be either the P or the R bands. And as soon as you see this, you just found out something about that RE. So here it is. If the upper state R minimum is bigger, then you get a bandhead and the other way around to the bandhead. So you can have this either way. Here's an example for oxygen. The ground state of oxygen is an X3 sigma minus G. You don't have to care about it. The value of B is 1.44. In the upper state A, B is 1.05. Notice how big the difference is. It can be huge. What does that mean? It means you could have a bandhead at very low values of J. And this leads to some issues. So the bandhead curves its roof. So this is what it looks like. If you plot versus M now, where the negative values are P branch, it's the R branch. There's the frequencies. So here's the null gap. Here's the lines of the R branch, and here's the lines of the P branch. This bandhead occurs at very low values of J. But it could have been in the P branch. So if I plot the positions of these lines, I can determine everything. If there's a null gap, then there's no Q branch, and there's never going to be P0. So here's the steps in the rotational analysis. We separate the spectrum from the bands. So you can go into one of those B prime, B double prime bands, and we just analyze the heck out of it. We tabulate the positions, we identify the null gap, and label these lines, which is not easy. And from that, finally, you get what you're after. You can get B. This is rotational analysis. Vibrational analysis, I have to look for the differences between the bands. But I want to show you an example for how we're going to go about doing this. If there's a bandhead, we know that the lines overlap. It's more complicated, but it also gives us a clue. If there's no bandhead, then the null gap, which is in the middle, is easier to find. If there is a bandhead, it's harder to find the null gap. If there's a bandhead, you start from far out in the wings and you work your way in using a method called constant second difference. You'll have to study this on your own to get this. You take the difference between two states, n plus 1 and m, that's called the first difference. You take the second difference, it's the difference between two first differences. And when you do that, you get this interesting result. But that second difference is a direct measurement of the parameter A, which I should put the alpha. That's the, remember, B is B sub B minus alpha B plus a hat. So here's a real example. Here's some lines that were observed in the spectrum of chlorine that were attributed to this electronic system and were decided to be in the 0-0 band. These are all the lines that were observed, and this is the spectrum. Use the wave number units here. This is what they observed. So you can look at this pattern of lines and you can figure out everything you need, or you could calculate it. The trick is, how do I do this? Our goal is to find DE and DE double prime, and then RE prime and RE double prime, and then null gap frequency after these information. So typically what you do is you go to the band head. Okay, the band head is at high energy. The band head is in R. Good, we know that. So now we found out the band head is in R. We don't know where the null gap is. So you go to the other end, and you work your way in, and you take differences. And you'll find that that wave frequency difference is 1.88, this is 1.7, this is 1.53. But what about T2? They look like they're the same. That's the trick. You go out to one end, and you find out what that difference is. Now you can work your way up, and you realize that if this was 1.53, the next one should be 1.36. So it must be this one. And so on. You work your way up, and then you turn around and come back, and in that process you'll find the band. So there's a strategy. And it's based upon this idea of a constant second difference. And from this you can, once you find the band, the null gap, then you can decide which one is the 0, the 1, the 2, or the 3. So you work your way in to find the null gap, and then you can label these lines. That's a lot of information. I spent an hour on that in my lecture. So from this, you find the null gap. I found 2A. It's there. I'm on my way to determining the numbers that I need. So there was no line here, but you can figure out where it had to be because of the constant second difference. So you find 0, you find 2A, which is just the difference between the two B's. Now I can use the method of common upper states to get information on B double prime. And if I have B double prime, I just solve for B prime, if that's related to 2A. But the constant second difference gives me the difference between the B's. Now I need to go in and measure one more thing, which would be the method of common upper states. That's how I go about finding. Now at this point I've got both these. You could have also done the method of common forces. Well, we haven't got the vibrational part yet, so we have to do the vibrational analysis. Now, when you do absorption, you get information on it's grouped in different ways. And this is put into a table. It's called, excuse my French, it's called the Delandres table. The French people pronounce it. I call it Delandres. Some famous French person. And they went in and they found the null gaps, all the null gaps they could find. And they entered it into the table, B double prime versus B prime. That's a number that they deduced from looking for the null gaps of all these spectra, and they entered these numbers. But we know that these G's can be written this way. Therefore, G1 minus G0, which is right here, is what? This number here, omega E minus 2 omega E. That number right here. G2 minus G1, that's here. This one is there. So I can take the difference between these. This is another method of common differences. So the difference between these two entries is omega E minus 2 omega XE. The difference between these is 2 omega XE. So by looking at these numbers and using this idea of the constant second difference, you can deduce the omega E's and the X's. So there's rotational analysis, there's vibrational analysis. And so you can work it along this row, or you can work it along a column. When you're working along a column, you're probing for a given lower state, you're probing different upper states. So you can only learn about the upper state. So you're going to determine the omega E primes and the XE primes. If you go horizontal, you're only probing the lower state. So you're going to only determine the XE double prime and the omega E double prime. Okay, so this would be a typical Delandres table, and you can use this information and you give a homework problem, and then you sort this out and you get all. So somebody looked at the spectrum, figured out all these null gaps, entered the numbers, and from this table, what do you get? You get the omega E's and the XE's with the lower state. vibrational analysis. We've already done the rotational analysis. Here's some typical numbers. So, you know, you look in here and you see this is 760, this one's 720. That means this is 40, 40, 40. So typically in a homework problem or an exam, I'll leave some gaps and tell them fill it in quickly they have to be in order to maintain constant secondaries. So you use rotational analysis for the V's, the alphas, and if you're good enough, you can determine these extortion parameters. Vibrational analysis. So you use emission. Emission is from a given state and you probe different lower states. Absorption, you're probing different upper states. So you use different strategies. So we're still after some dissociation energies here. Here's some typical analysis. Band origin. We find that zero is right here. That gives us the TE. Now we probe these vibrational things and get the dissociation energy. So there's just strategy, strategy, strategy. You're not going to actually do this. You're just understanding that this is why spectra look like they look like. You're more interested in how do I measure CN. Usually you go find a paper where somebody measured CN and you read about how they did it. You decide if you're going to do the same thing. Or you want to measure temperature. Or you want, so you usually are riding on the shoulders of other people who have done this for their own purposes. But this is how the properties of molecules are determined. Dissociation energy is really important. So we're interested in finding the dissociation energy. So if you wanted to know what's the dissociation energy of molecular oxygen, well, you usually want to do a homework problem. What's the chemical equilibrium for oxygen at a given temperature and pressure? You have to put in the dissociation energy. So you need to know the dissociation. How do we get the dissociation energy? There's different ways to do this. So we've done rotational analysis, vibrational analysis. Might do the bond dissociation. Do this right here. Yeah. Okay, so there's different strategies, and I want to introduce you a couple of famous ones. We're just one method from the chemical. So here's the chart that shows you the definition of these terms. We could use this kind of a pattern to get these numbers and deduce dissociation energies. We can do it in emission, absorption, but basically it's structure. Structure of these patterns gives you these numbers. We can use this sort of analysis for vibration. But there's what they used to in the old days with film. So people spend a lot of time interpreting. Okay, now I want to do a famous thing. This is not the way people actually determine dissociation energy, but it's a nice thing to know. Why do we care about dissociation energies? Because in thermodynamics, heat formation and reaction are important to us. Also in chemistry, the rates of reactions depend upon energies, associated energies. There's a famous method called Bird-Stoner method for getting the dissociation energy. It's called the constant anharmonicity model. So we now say that G is a function of the harmonic term and the first anharmonic. We neglect the other. Therefore, G of V plus 1 can be written. I can take the difference in G between V plus 1 and V, and I get these two terms. And the main thing is that you notice that this term is dependent, this is the constant, and this term depends upon it. So delta G is a linear function of G. Therefore, it's basically saying that these levels decrease in spacing linearly with V. So I can use this Bird-Stoner concept and write this delta G and ask, well, when does delta G go to 0? When do the spacings go to 0? And I can use that as a definition. So you can solve for the energy at which this occurs. Or you can look at it this way. Here's delta G as a function of V. And when it gets to 0, you're done. And that's the dissociation energy. It's an approximation. It's the constant anharmonicity approximation. So if you do that, you can get the dissociation energy, and it's omega E over 4x. Remember, x is a small number. If you think about it, this is also the area under the curve. So the way to thinking about it, the math is the same. The energy is given by omega E and X. The real molecule actually does something more like this. It does not stay constant like harmonic. It increases. So the Bird-Spooner method is going to over-predict the. And here's an example. Here's an example for HCl, where omega E is measured at 2990, Xe is. Where we get these numbers? We did the row vibrational analysis. You take the row vibrational analysis and the Bird-Spooner concept. You can solve for the dissociation energy. If you do this, you get 427 kilojoules per mole, whereas the actual number is like 513, so it's off by about 20%. So it's not too good. But it's famous. And what it stresses to you the relationship between omegas, X's, and D's. There's another approach. This is a good approach, but it's not used very much. If we think about a molecule like iodine, and we write the, if you go to chemical thermodynamics, the equilibrium constant for pressure, which is the pressure of the products, reduced coefficient. In the case of P, the equilibrium constant for pressure, Pi squared over Pi2. So Kp is a function of temperature only, and delta A. So this is the Van population. The derivative of the log of K sub P, delta H is RT squared. Well, the K sub P is e to the minus delta G over RT. So anyway, there's a relationship then between populations, partial pressures, and the dissociation. So if you can measure in an equilibrium situation of known total pressure in the populations of these two species, and you know the temperature, you just find the delta H. So this is pretty good. We've used this to measure partial pressures of species and use this to solve for equilibrium. Here's the most important example that I know about. I had a student who was measuring the evolution of OH behind shock waves in hydrogen and oxygen. So at 2590 Kelvin in the atmosphere, 4,000 parts per million of hydrogen, 4,000 parts per million of oxygen, with hydrogen rich. This is the evolution of OH versus time. I'm not interested in how long it takes. That would be the ignition delay. I'm interested in how much OH is formed. That's a so-called quasi-equilibrium region of this program. And so that, if you calculate that using, say, GRI map or detailed chemical mechanism, the inside of detailed chemical mechanism is already embedded in thermodynamic tables. Those tables include heats of formation. So if you change the heat of formation, you change the answer. So these are the simulations. The measurement is the solvable. Simulation is with a heat of formation of OH of 9.403. And then the perfectly agreeing solid line is if you take the heat formation of 8.887. Well, everyone accepted 9.403 until about 10 years ago. We kept finding this problem, and I kept thinking the student doesn't know how to measure OH, how we're always off by 8%, tried everything, couldn't find a problem. Somebody finally said, well, is there any chance the heat of formation is wrong? Can you believe heat of formation with OH would be off? You wouldn't think so. Well, about the same time, somebody at the National Laboratory was compiling something called an active chemical thermal kit. And he concluded that somehow an error had crept into this and it was actually 8.9. Exactly the same number. Amazing. His number is probably slightly more accurate. But the point is, you could use concentrations of species. Now, how do you make a measurement of the species? This is tricky. How do you get the absorption coefficient? Usually, we would do an experiment where the thermochemistry is known, produce a known amount of the species, measure the absorption to get the absorption coefficient. So in order to do this, we have to know the absorption coefficient that then measure the species. So there are other ways to get the absorption coefficient. I won't go into the details. So they're known to about 3%. So we knew that the absorption coefficient 3% had this 8%, 9% problem. And if we took our best value of the absorption coefficient, we got this answer. So you can use thermochemistry. If you can measure the species, you can use thermochemistry. Then you can use species measurements to do thermochemistry. This was just a plot. Rusik was the guy who did this from his active thermochemical table, I guess for 13 years. Anyway, we've got good agreement. Here's our data. Well, I think I'm running ahead of it. So what we've done ionic moments. Somebody asked about Collier. So we're going to go to Collier. Much harder. Unfortunately, in combustion gases, the molecule is pretty small. It's not how complicated formation is. Of course, we have to accept certain rules. We have to accept the notation. Okay, any questions?